So these are new VMs today, so we're going to have to reclone Spack. Git clone. I use branch depth 2 just for speed. Branch releases / v1.2. That's the release branch for the latest release. And once we've got that cloned, we will source the Spack setup script. And then in the basics tutorial yesterday, we did some sort of basic setup, Spack mirror add unsigned tutorial. We'll just giving it the arbitrary name tutorial, and it's located in /mirror in these VMs. So that's how we find the binary packages. Spack bootstrap now. This just tells Spack to go get Klingo and a couple other things, right? We're seeing patch elf show up that Spack needs at runtime. And then the last thing we will do is Spack compiler find. And this just tells Spack, go find what compilers are available on the system, and this will get us back to the state that we were in at the end of yesterday, except we've got less software installed. So we're going to start today with what we call our stacks tutorial. And fundamentally, this is about how do you deploy sort of combinatorial suites of software. I have some amount of software that I want to deploy with every MPI library on my system, with every compiler on my system. How do I go about that? In the process of talking about that, though, we will also be talking about bootstrapping compilers and how do I generate modules for the things that I've created and a lot of things like that. So let's just jump in. Our goal in this sort of example will be an environment with 2 MPI libraries, 2 LAPACK providers, and we're going to install netlib scalapack for all of those. So spack env activate -- create just lets us skip a step, and we're going to make an untracked environment in this directory ~stacks, and spack env status, there we are. So I will use spack config edit I will export my editor so you don't have to watch me struggle with VI. And now I will use spack config edit to create this environment. I'm going to kill the comment at the top since I don't think that's helpful. Get rid of that as well. Okay, and what specs do we want in here? Well, to start with, we're going to do some bootstrapping. We're going to see, say, GCC at 16, built with GCC at 15. We want a newer GCC compiler than what's available on the system. And we also want lmod at this particular version, 8.7.67. And we will also build that with our older compiler. And we're going to turn off the view generation for now. Because we're going to be putting things that won't be compatible in the same view together. And then towards the end, we'll bring the view back in and we'll show how we can make a view robust to this sort of combinatorial software stack. So let's concretize this. And as soon as it's concrete, we'll install it. And previously, when we talked about environments, or when we talked about installing things in general, we said the compiler has to either already be installed or be an external or available in a binary cache, something where we have a concrete spec for the compiler already. And when you go to bootstrap a compiler, that's annoying. I would like to be able to describe, I want these things built with this new compiler. And so we have a functionality, a feature to be able to do that in Spack, and it's called Spack groups. So I'll open up the environment again. And we're going to sort the specs in this environment into two groups. We're going to say group compiler, and that will have its own specs list with these things built with the system compiler. And we'll have a group for our software stack. We will say that group needs the group named compiler. And the specs in it will do netlib scale-a-pack, built with GCC at 16, depending on OpenBLAS and OpenMPI. So we've not done the combinatorial explosion yet. We're just building one netlib scale-a-pack. But we've said we have these two spec groups. This one, for our software stack, needs the compiler group to be concretized first. And that allows us to then reuse this compiler spec, even though in an individual solve, you need to only be reusing concrete compilers. All right, I'm going to close that. We're going to Spack concretize again. And we'll see what happens. Okay, the compiler group gets concretized. When that's done, the stack group will get concretized. And then we will see three specs, two from our compiler group and one from our stack group. And there we have it, just as we expected. Now, we used a direct constraint to pin the compiler in each of these groups, and that's fine, but I don't like having to repeat that all the time. So we are going to take advantage of another feature of these spec groups, and we're going to say override. And we can override some of the config here. So we can say packages C prefer GCC at 15. And I'm going to copy that block because we're going to do the same thing for Fortran and C++. Okay. So this should look pretty familiar from the config section earlier. Now we don't need to say which compiler to build with here. These things are going to prefer GCC 15. And we can do the same thing in the stacks section to say prefer GCC 16 throughout. And now I can get rid of this compiler constraint here. There's nothing wrong with doing it directly with the compiler constraint. It just means you have to repeat yourself for every spec. So any config that you can write in a normal section of your config, you can also override for a particular spec group. Now, let's also talk about the concretizer options here. So we're going to add a second spec for netlib scale-a-pack. This one we're going to build with OpenBLAS, so the same as before, but we're going to build it with mpitch. So one difference. So we can't use unify true like we have in the past here anymore, right? That's going to say, I want to unify all of the things in this environment, or in this case, in this group. I want them all unified, so every package name is going to appear at most once. There's some exceptions for build dependencies, right? We model the unification set, which is the link and run subdag plus the direct build dependencies, and that's the space that we unify on. But we've now explicitly asked for something that can't possibly be unified, right? You can't put two different netlib scale-a-packs in the same unification set, so we're going to have to change this. So we'll come back down to our override section. And we'll say in the concretizer section, unify false. Now I'm just going to go check and make sure that I don't have tabs that I didn't want, because that will mess up YAML. Okay, there we go. So we've said unify false. We're allowed to duplicate specs in this section. All right, now we will concretize. And we will see one additional spec. We added the one netlib scale-a-pack spec, and the other change that we made was just refactoring the environment, but did not actually change which specs were involved. We could, instead of using unify when possible, use unify false, we could use unify when possible. With that option, Spack is going to see how many of the things it can concretize together and concretize those together, and then pick off smaller and smaller groups that can be co-concretized. Generally, that option is great for things that have very minor deviations only at the top of the stack. But if you're going to build, say, with an entirely different tool chain, that's probably not the best option. So let's look at our environment again. And we could start adding more and more netlib scale-a-pack specs here. But at some point, that's going to get a bit tedious. We just want to add another BLAS and LayPack provider. Maybe it would be fine. But let's start cleaning this up right now. So we're going to say, here we have a matrix. And the components in this matrix, the first one, they're all netlib scale-a-pack. And we have things built with OpenMPI and things built with mpitch, which is what we had before, and things built with OpenBLAS. And now we can add, at the same time as doing this refactor, things built with netlib LayPack instead of with OpenBLAS. So here, all we've done is we've added two builds, the same two MPI builds, but with netlib LayPack instead of OpenBLAS. and we've refactored it. And obviously, this is a bit of a toy example, right? We could write out for ourselves. But when you start using 5 or 6 different MPIs, 5 or 6 different compilers, this matrix syntax will really help you out. So we'll concretize this as well. And because we haven't changed the compiler group at all, we don't need to reconcretize it. You'll see it doesn't show up in the output. And we concretized two specs because there are only 2 new specs. We also didn't change these 2 OpenBLAS specs. So we only concretized the 2 new ones, and there we go. Okay. That's all nice. But what if we want to start reusing this list of MPIs for the things that don't depend on BLAS or LAPACK, or maybe the other way around? To do that, we will need to create some definitions. So definitions in a Spack environment are just lists of specs, named lists of specs that you can then reuse elsewhere. So we have our MPIs, OpenMPI and MPitch. We'll have our LAPACKs, OpenBLAS and netlib LAPACK. And we'll have our MPI packages. And maybe this is a giveaway for where we're going to go next. Netlib Scalapack is our only package that we're building. And then we can come down here, and in our matrix, we can say, okay, build me my MPI packages. And a note on the syntax, these are splatted in. So you still put a list containing, and that's where you dereference the list. And these are splatted into place. It's maybe not the most intuitive thing the first time you work with it. I promise it works out better than doing it the other way. And here we're going to dereference the MPI list, but we're going to do it as dependency constraints. So we can say, give me my MPI list and turn each spec in that list into a dependency constraint. And we'll do the same thing for our LAPACKs. So this allows us to write our list of MPIs, and we could have, say, another group in which we install the MPIs as the top-level packages, and then in this group, we're using them as constraints. And just to confirm, we'll do a Spack concretize. No new specs to concretize. We didn't actually change this environment at all. We just refactored it a bit. So now, as we kind of gave away with our naming earlier, we're going to add some serial packages. And by some, I mean 1. And that's going to be PySciPy. There's our serial package. And now we're going to need another matrix. Now, we could put this in a different spec group if we wanted to, but since we want the same configuration as before, we'll keep it all in one spec group, and we'll just add a second matrix. And the things we want in this matrix, we want to install PySciPy, which we've defined as our serial packages. And we want the same combinatorial expansion on LAPACKs, but there's no MPI dependencies here, so there we're done. And in this case, we actually also know we don't ever want to build SciPy with netlib LAPACK. So here we go. We will exclude SciPy depends on netlib LAPACK. So we expand the matrix, and everything in the matrix gets compared against the exclude specs. And if the abstract spec from the matrix satisfies the exclude, it will be excluded. Notice it's the abstract spec. So if we left LAPACKs blank and let Spack choose to concretize, it could still concretize to netlib LAPACK, even though it was excluded. Now, I mentioned something about a toy problem earlier. This is obviously even more of a toy problem. This entire matrix just defines one spec, but it's here so that we learn the syntax. We concretize this now. We will see one new spec be concretized, and this is our SciPy built with OpenBLAS. Our SciPy built with netlib LAPACK was excluded, and that's all that we had added through that matrix. Now, the last thing we're going to talk about for how we build up the list of specs to install are conditional definitions. So if I open this file back up, if you define the same name twice, so we've got MPI's mpitch and MPI's OpenMPI. If you define the same name twice, those lists are concatenated. So this, I haven't changed our environment at all yet. But what I'm going to do next, I'm going to add a condition on this second definition. And here in the script, you can see all of the restricted set of variables that you have available to you. The when clause is just Python code with this restricted set of variables available that you can define when something will be used. In this case, we're going to say env.get. So this is checking the environment variables. Spack stack use OpenMPI is the variable we've defined. Now, if that's not defined, we need to handle that gracefully, so we'll put in a default. So we'll get the environment variable Spack stack use OpenMPI, or nothing if it's not there. And if that is equal to 1, we'll use OpenMPI. And if not, we won't. All right. So we will now Spack concretize. And we haven't set the environment variable. This says no new specs to concretize, but 2 specs were removed. We can check with Spack find -c for concrete. So we don't need it to be installed for it to show up in the find output now. So we've said show us the concrete specs. And L, so it shows us the hashes. L for long. And we'll just look at our netlib scale-up specs, because those are the only ones that are affected by MPI. And you can see we only have these 2 netlib scale-up roots because we're not using OpenMPI anymore. Now, if we set Spack stack use OpenMPI to 1, and we concretize again, it's going to take a second to concretize these 2 specs, but we'll see them back just as they were before. So now our environment is back just the way we had it. but the concretization is now contingent on this environment variable because that's the way we put it together. So that's everything on how we are going to construct the specs for this environment. And now we're going to install it. And for the rest of this section of the tutorial, we're going to be talking about how to expose these specs to your users. Generally, with these large software stacks, we're not just installing them for ourselves. How do we expose this to users? And there's two primary ways that you do this, through a view or through modules. We'll talk about the view first and then talk about the modules. Here's a couple other useful features you can do with a stack once you've built it. You can push it all to a mirror, and you can use that to pull all of these down on another system. This is what we've done to prepare the binaries for the tutorial, and we'll talk more about this in one of the last sessions today, talking about binary packages. For now, we're going to move on to talk about views. So Spack config edit. Previously, when we've had a view, it's just been a single directory with everything in the environment put in it. And if we tried to do that now, we would start symlinking multiple netlib scalapack packages into the same directory. They have all the same files, they'd all conflict, and Spack would yell at us. So what else can we do? Basically, there are two ways that we can deal with this. Either we can curate what goes into the view to a set of things that are all compatible, or we can give the view some structure to say, here's how you split the things up. And for this example, we're going to do both. So the first view we're going to write, we're going to call it default. And the default view is the one that gets put into all of your environment path variables when you activate the environment. So if you say Spack env activate, right, that makes all of the software available to you through path. And that's using the default view. That's the view that you get if you just say view true. You get the default view in a default location. So for the default view, we're going to say where we want it. And we're going to put in only a compatible subset of our software. So we're going to say only include the things built with GCC at 16, and exclude the things built with mpitch and the things built with netlib laypack. So we're taking only the things built with GCC 16. That means only the things that have a compiler at all and are in this stack, which SciPy and netlib scalapack both do use the compiler. And we're going to exclude all of our duplicates, because all of our duplicates are along one of these two axes. So there's our default view. And we're going to name a second view full. This name doesn't matter. The only special name for a view is default. We're going to put this in a separate directory. And instead of selecting and excluding what goes into it, we're going to set up projections. So the projections are, how do you translate a spec? Sorry, my light will turn off if I don't move. How do you translate a spec into a subdirectory within this view? And these are evaluated in order. So we have to put the most specific ones first, and then it'll fall through. So we'll say the things that depend on both MPI and laypack, we're going to give those a name, a path that has the package name. And then at the next level, we're going to say the name and the version. And we're going to look at the dependency that's providing the C virtual and give that name. So that's effectively the compiler. Now, we haven't confirmed that everything that depends on MPI and LAPACK has a C dependency explicitly here, but we know that all of our packages that are building with these virtuals also use a C compiler. And we'll look at the MPI dependency, and we'll do the same thing for that. And we'll get the name of our LAPACK provider and the name and the version of our LAPACK provider. All right, so that was a lot. We're going to go a little faster on this next one because then the things that don't depend on MPI but do depend on LAPACK, I'll copy and paste this. But this is the same structure, just remove the MPI references, right? The name, the version, the C compiler name and version, the LAPACK name and version. And then if it depends on C, if it uses the C compiler, we will add, again, this is the same thing, just removing the LAPACK information, just C. And we'll do the same thing for C++, in case we have something that depends on C++ but not C. And similarly, for Fortran. And then lastly, we have a fall through for all. And we'll just put it in a directory based on the name and the version. So if I close out of this, I will do Spack concretize again to trigger a reevaluation of the view. And there are no new specs to concretize, but we do get these views constructed. And we'll take a look at these views. We can look in stacks views default. This looks like a normal Unix prefix. It's got bin, lib, include, etc. And if we look in the lib directory, we've got all of this stuff from all of the things that we depend on. Here's some MPI libraries, here's some expat libraries, whatever, all of those things. And if we look at the full view, here we just get a list of all the packages because the name is the first thing in all of our projections. And if we look at one of these packages, say GCC, we've got our GCC 16 and its compiler was GCC 15. So that's the naming here, right? Name version, name slash name version, C compiler name, C compiler version. And if we look in there, again, we've got a Unix prefix. Here's the bin directory with GCC, G++, G4tran, everything we'd expect from an installation of GCC. And these are all, the files here are all symlinks back to the underlying installation. You can change that. You can configure that to be hard links or copies if you need to. Now, the one thing I will say about this is this view feels pretty polluted because we don't need all of these things that we didn't actually say we cared about in our environment in this view. So we'll make one last edit to our views, Spack config edit. We'll let our full view stay the same, but for our default view, we're going to say just link the roots. So link : roots. And we concretize again. It only needed to update one of the views. Didn't update the full view. And now we only see a lib directory because there are no binaries for SciPy or netlib scalapack. And if we look in that lib directory, we see the scalapack libraries and the Python site packages dir with SciPy in it. And here's all the internal bits of SciPy. We could look at the full view again, but there's not a whole lot changed there. There's in fact nothing changed there. So now let's move on to talking about module files. So this is fundamentally our other way of exposing the software to users. A view can give them a nice path to find it at. Module files, most people in HPC are pretty familiar with. So it's a good way to expose software to users. And now we get to do maybe my favorite command in this whole tutorial, just for the file name that it gets. We're going to source the module setup script. So spack location -i lmod /lmod /lmod /init /bash. And so now we have modules available to us as a program. So now let's go back to our environment and we're going to configure it to add some modules. And just for clarity during the tutorial, to keep things a little less cluttered, I'm going to turn the view back off. But there's no reason that you couldn't have a view and modules at the same time. They don't disrupt each other at all. It's just to keep this all close to being on a single page. So I'm going to create modules. I'm going to name a module set. I'm going to call it default. And that's just to make the Spack commands for managing these modules manage this set of modules by default. You can name your module sets anything you want. You can have as many sets of modules as you want. And when we do a Spack module lmod refresh, you just have to tell it which set you're talking about if you don't mean the default one. We're going to enable lmod. Spack can also generate tickle module files. We're going to demonstrate lmod. The core concepts are pretty similar. And now we need to say where to put our module files. Our lmod module files are going to go in a directory creatively named modules. And then we have some lmod specific config. We're going to say we want a hierarchy for our lmod modules that includes the MPI and the laypack. And you can put any spec here. In this case, they're both virtual packages, so you can swap out the providers, but you could also swap out on, say, different Python versions. And then there's some things that we want to be in core in the lmod hierarchy. If you're not familiar with lmod, this terminology will make more sense in a minute when we start looking at the generated module files. But we're going to say anything built with this GCC 15 compiler, we want in core. And remember, with the structure of our environment, basically we built some some basic tools. The compiler, we bootstrapped our compiler and we built lmod with GCC 15, and everything else is with the newer compiler. So there's our configuration. And now we are going to regenerate the modules. So we're going to Spack module lmod refresh. And I left a tab in here on line 56. No, on line 57. Okay, I think that's the only one. And it says, do you want to regenerate these modules? Now, considering we don't have any old module files that will be blown away, it's a pretty easy answer. Yes, we want them. And now we will have to tell the module system to use our new modules. So we'll do a module use. Stacks modules. And Spack automatically puts onto the platform and the operating system and the architecture family into the module file name. And we only have to tell lmod to use core, and lmod will handle pulling in the other module files. So if we do a module avail, well, these aren't the prettiest module names I've ever seen, but we do have modules for a bunch of things in core. And these mostly look like they're the dependencies of GCC, right? I recognize MPC, MPFR, and the dependencies of lmod, Lua, some Lua things. And then here's our core compiler that we built up with these things. If we do a module load GCC, now module avail. This is the nice thing with lmod. We get these hierarchical modules. So now that we've loaded GCC, we can see all of the things that were built with GCC. And we can module unload GCC. Okay, so we've got modules. Great. That's not how I would want to expose them to a user. A lot of the dependencies of GCC were cluttering up the list with things that I would not want to expose to my users necessarily. The hashes in the module names, we've already curated this environment for our users. They shouldn't be needing to specify things by Spack hash. So maybe we'll get rid of those. And some modules might need some more configuration beyond just exposing them in the path to the user. We might need some MPI tuning parameters, things like that. So let's go and do this. So Spack config edit again. And we come down to our here we got this core compilers bit that Spack automatically added. This just says any external compilers it found on the system. It'll call them core compilers. We can ignore that for now. It'll, since we're going to be excluding all of these anyway, they're not in our environment. Okay, so we're going to set the hash length to 0. We don't want to see the hashes. We are going to exclude everything built with GCC at 15. And we're going to exclude autoconf because it happens to be that there's multiple versions of autoconf around here, and we don't want to have to distinguish them, and we know the users don't need to load autoconf. Now, if we just excluded everything built with GCC at 15, we would, of course, not see our compiler that we bootstrapped in the compiler spec group. So we do want to override those excludes with an include for GCC. Any GCC that we built, whatever compiler we built it with, we want to see that. Now, we might have a policy that for all of our packages, we want some more environment variables. So we can go into the environment, and specifically in our case, we want to set something. So there's a bunch of operations we can do. Set, prepend path, append path. We can unset or remove things if we really need to, although that's pretty rare in a module file. And the name that we want to set is parameterized by the name of the package underscore root. So this is a common thing in modules. We want GCC root, we want netlib scale pack root, etc. With these parameterized environment variable names, Spack will automatically uppercase the entire name. And we can grab the prefix from each spec. With these parameterized things, you can specify any attribute on the spec object. So if you look at the Spack API documentation online, anything that you can reference there, you can put in one of these brackets. It's the same thing for the projections that we used before. And maybe for OpenMPI, we need some more specific stuff. So we also want to set some environment variables for OpenMPI. And what do we want to set here? Well, slurm MPI type PMI2. And then we want to set this very long variable that I am going to copy and paste in. OMPI, MCA, BTL, OpenIB, warn default GID prefix. So a couple of variables that control how OpenMPI behaves. And then projections. This is the same syntax as before, but because of the hierarchical modules, we don't actually have to do a lot here. In fact, we're just going to say name and version, and that's enough. And in this case, we would have been fine not specifying this. This is the default projection for LMOD modules, but just to show that this is a thing that we can set as well. So Spack module LMOD refresh. We'll add the -y argument to say, yes, we know it's going to do some things we really want to. And we're going to add delete tree. We don't only want to override the modules that we've changed. We also want to get rid of the ones that we've stopped generating for. So that's why we need the delete tree argument this time. And now we have modules more like what we would expect. We have our GCC modules. If we module load GCC, we get the things that we built with GCC. Module load OpenMPI, OpenBLAS, PySciPy. Module avail again. And you can see we have one of our netlib scala packs available. We've loaded SciPy, which auto-loaded NumPy, and we've got a bunch of dependencies loaded. Now, if we module load netlib scale-a-pack. Lmod will actually help us out here and will prevent us from getting things cross-loaded. So if we do a module load mpitch, you'll see, okay, netlib scale-a-pack, they actually swapped out which one we had loaded. It's not this one anymore. It's the one now for for mpitch and OpenBLAS. And if we do a module load netlib laypack, we'll see a bunch of modules are made inactive because SciPy, which we had loaded, is not compatible with netlib laypack because we excluded that combination. And netlib scale-a-pack is reloaded. So just a little bit of the fun of using this hierarchy with Lmod. But yeah, that's mostly it for the stacks tutorial. We talked about spec groups with the needs so that we can bootstrap a compiler, the override to control the configuration within each one. We talked about spec matrices and definitions to build out the combinatorial environment. We talked about conditional definitions to be able to customize the environment per machine, per environment variable, etc. And then we talked about how do we expose this to our users, file system views and module files. And with that, I will turn things over to, I believe it is Caetano, who will be talking about writing your own Spack packages.
So for this next section of the tutorial, we're going to be talking about creating our own packages. So far in the environments tutorial and the software stacks subsections, we've been consuming packages by compiling them, installing them, and generating views, generating modules with them, linking libraries against them, things like that. But at some point, if you have your own software that you want to package into Spack and make available to a bigger community or have it used by some of your internal users, you'll have to do this by creating a package for it. So in this section, we're going to be creating a package for MPI leaks, which is an MPI debugging tool created here at Livermore. So just be aware of that. So to give a general overview of what a Spack package actually is, at the end of the day, they are installation scripts that are recipes for building, installing, and testing software. And they define certain properties of the build, like where to find the software, what dependencies the package should actually use, any build options, we call those variants, any constraints that are known between between the software you're packaging and other software available in Spack, any known requirements like any platform requirements, any OS requirements that you want to make users aware of, and any build commands that you need to have Spack propagate down to the configure, build, and installation process so that the software will work functionally for the user when they're installing it with Spack. And I just want to be clear, I think this is pretty obvious based on Spack's philosophy, but these package recipes are designed to be as portable and generalizable to a variety of platforms, OSs as possible, in addition to things like compiler and GPU architecture support. So you'll have to keep a lot of things in your head when you're developing these packages, but the idea is that someone, if your software supports it, will be able to concretize your package with Spack and find dependencies successfully without needing to deal with the pitfalls of building a package from scratch and manually debugging that. So in order to avoid generate or modifying the existing Spack installation that we have, we're going to create our own custom package repository for this subsection of the tutorial. So we're going to use the Spack repo command to do this. So let's go ahead and write Spack repo create. And then we're going to create this in our home directory, my packages, and then we're going to call the repo tutorial. So we next are going to add it. We're going to register it with Spack. So we'll do Spack repo add, and then we'll do home, and then we can have it autocomplete here. So it's home, my packages, Spack repo tutorial. So at this point, Spack has registered this repository, and we can verify this by doing Spack repo list. And as you can see here, we have our built-in repository, which is where all the packages we've been installing so far have been sourced from. And then we have our new tutorial repo. We can see some basic information about how the repos are configured by running spack config get repos. And as you can see, tutorial, the one we just created, it will take any packages within this local directory here. And then the built-in repository, it was created based on this Git repo, and will pull from the releases branch that's specified here. So there are many ways to host repositories. You can have a bunch of local ones. You can host them in a Git repo, among other options. So on to creating the actual package file. We've talked about this before, but we're going to be doing a lot of editing in this subsection. So if you don't want to use whatever the VMs are going to default to, so probably Vim, you'll want to change one of these 3 environment variables, likely editor. We'll get you there to Emacs or whatever your preferred editor is. So just a heads up on that. So for this subsection, we're going to suppose that you want to install MPI leaks, but Spack doesn't have a package for it, so you're going to have to create one. Spack's create command will accept a few different parameters that Spack will ingest and use to create some scaffolding out of. So you can do things like give it the location of the code, and Spack will download it, analyze it, see if it can detect things like the build system and things like that, and create like a basic template that you can then use to edit the package further based on the knowledge that you have or that you can get in the documentation of the software. So taking a look at the MPI leaks repository, and at this point, it's probably a good idea to open up a new window here so that we can look at them side by side. So I'm going to make this a bit smaller. Oops. So the MPI leaks source code is available as a tarball. So let's go look at the releases here. And then we can see that the developers of MPI leaks have released a tarball here. So we can pass the location of this tarball to the Spack create command, and Spack will download it and do some analysis to create that scaffolding. So let's start off by writing Spack create, and then we'll call the package tutorial -MPI leaks. We're not going to call it MPI leaks because the MPI leaks package already exists in the built-in Spack repository, so we don't want to overwrite that one, cause issues with it. And then we're going to specify namespace, which is essentially an alias for a repository name. So we want it to be created under the tutorial repo, and then we're going to paste in the link to the tarball. And then Spack will download the tarball, and then that was pretty quick. It created this sort of skeleton template. So it gave, we have a couple instructions here about how to install the package and then how to edit it with the Spack edit command. We can see that it detected that it was an AutoTools package. It inherits from that class. It found the URL from which the package should be downloaded from. And it has a few like these fix me comments here for things that we need to look at the package and fill in. So based on what it found, it also detected we need C, C++, and Fortran compiler to actually build the package, and has a couple autoconf specific methods here that it filled in. So there's still some things that we need to change here to make it a more complete package and a package that will be up to snuff if you decide to submit it as a Spack PR. So, but we'll get into that a bit later. And the parts of the package that we're going to be editing today are highlighted here. So we'll get into that in a second. So Spack auto-detected when it downloaded the tarball. It detected that it was version 1.0, which it found from the file name of the tarball, and then it also checksummed the SHA-250. We got the SHA-256 checksum from that tarball. So this is a pretty important aspect of how we track the provenance, the security of these tarballs, and we do a check to make sure that the tarball hasn't changed based on what the recorded checksum is for the package. And at any point, you can use a couple helper commands to ensure that the version or the checksum that's recorded in the package still matches what's in the tarball. So we can just double check that Spack checksum the tarball successfully by running Spack checksum tutorial MPI leaks. Then we'll checksum the specific version. So as we can see, and I'll open up the package once more just to verify, but it starts with 2E34. So we'll do Spack edit MPI leaks, tutorial MPI leaks. And we can see here that it matches the SHA-256 argument on the version directive. So before we make any changes to the repository, let's just try to make let's just try to install the package and see what happens based on what Spack was able to detect using the Spack create command. So we'll do Spack install tutorial MPI leaks. So that'll concretize this pretty basic spec, try to find out what dependencies it may need, download those dependencies, and then install them likely from the build cache. So all that's working fine, and then it's on to the configure step of our package, and then we hit this error. So it says something about it's unable to locate an adept utils installation, and Spack will automatically print out the last lines of an error message so you can get a good idea of what you might need to debug off of. If there's an error in the package recipe. So we'll need to deal with this in just a sec. But for the time being, let's continue on and editing the initial package by filling in some of the provided placeholders and document some key information about the package, just to make sure that we have everything we need. So we'll start off by running Spack edit tutorial MPI leaks, and then make sure that you have the MPI leaks repository here open in another window so we can get some info about the package. So the first thing we're going to do is remove this boilerplate comment. And then let's add a better doc string that is an accurate representation of the package. So we can usually get a pretty good description by taking what's under this about subsection on the GitHub page for the repository. So we have that there. And then the home page can usually be the direct link to the Git repo. So we'll do homepage equals the URL here, and then delete that example. We'll remove this for now. And then for maintainers, this is pretty important if you're deciding to upstream these changes or a new package to our Spack packages repository. So if you are the main author of the software, or you're someone who's typically involved in the development of the software and have some Spack knowledge, you might want to consider becoming a maintainer for the package, meaning that upon creation of a PR that edits this specific package, your username will be requested for review, and the Spack maintainers will ask that you provide some feedback in case someone's needs some advice about how to package it, or you have better information about how to do something for this software. So I'll just add my own username there. And then the next important thing is adding some license information so we can check this license.txt file. So it's a BSD license. So we're going to edit the directive here. I'll add some provenance for the license here by just saying that I'm the one who checked it. And then we'll add the SPDX identifier for the BSD license, which is just uppercase BSD. So now we have Spack automatically filled in the version directive, and we already confirmed that the checksum matches the tarball that we expect. So the package should look like this, with the changes to the doc string, to the homepage, the maintainers directive, and the license. So let's close out of this, and then we'll see what Spack can do with this additional info that we add to the package. So the Spack info command, if you run it, we'll do Spack info phases, and then we'll do tutorial MPI leaks. So we can see that this is an auto tools package. We can see that the doc string that we add to the top of the package from the description in the GitHub page is shown here. So anyone who isn't aware of what this package does, wants to find out where it gets downloaded from, what the homepage is, the Spack info command is a pretty useful place to do that. Shows all the dependencies, and because we specified the phases flag, we can see what phases this specific build system will go to actually build the package to completion. So you can have a better idea of when the package is attempting to be installed, what phase you might expect next. And we also have some transitive dependencies here that are due to the fact that we have an auto tools build system. And then you can see things like the license. So Spack info is a useful tool for, if you just want to know more about a package, what it depends on, what you might expect to happen when you actually want to install it with Spack. So at this point, let's add the dependencies for this MPI leaks package. So just going to read through the README for a second. Obviously, this is going to depend on MPI. And we can see here that the configure call requires adept utils and call path, which luckily are already built in Spack. So let's update this. So we'll open up the package again by running Spack edit tutorial MPI leaks. MPI leaks. And then we're going to add our depends on directives here. So it'll be simple as adding depends on MPI, depends on adept utils, and then depends on. So we knew in advance that these packages existed. You can do things like run Spack info, run Spack list to see what packages are available in Spack, to see if the software that you're trying to package are already available in Spack. So if they weren't available, we'd have to go in and create packages for adept utils and call path. and potentially their dependencies if those weren't packaged as well. And I just want to make a quick note about the MPI dependency here. So this is known as a virtual dependency, meaning that Spack can satisfy this dependency on MPI with another package that's known as a provider. So that can be something like OpenMPI, MVAPITch, MPitch, things like that. And they're called providers because they implement the virtual dependency, in this case, MPI's interface. So any available MPI in our environment that can satisfy this will likely be filled in when we ultimately concretize the package. So let's close out of that, and then we're going to go back and attempt a reinstallation of MPI leaks, and maybe that configure error that we saw before will go away because I think it referenced something about adept utils missing. So now that we can have Spack compile adept utils and have that available in the build environment, that could potentially solve some of these issues. So we're going to wait for that to reconcretize and install those dependencies, adept utils and call paths. So we have these installing here. We have OpenMPI installing. We have MPI leaks going through its configuration process again. We can see here that, okay, it failed again. So at this point, we are going to have to do some more debugging about what's actually going wrong in the build environment when this package is I think in the configure step. So we have a couple options for this. We can look in the build log for more details, which Spack will conveniently print out for you at the end of each error here. So we can see that this is the location of the log. And we can also try to perform the build manually as if you were trying to build this in a pre-Spack era, with manual configure steps, things like that. So let's take a look at the build log. So I'm going to copy this, and then you can use less or cat to bring this full file up. So I'm just going to scroll down here, see if there are any details that we can see here, but looks pretty standard. And yeah, we basically don't get any additional information from this because we already saw this configure error, and it was unable to find the adept utils installation. So we can try the next thing, which is to do a manual build. So let's change into the staging directory of tutorial MPI leaks. So you can do that with Spack CD. So Spack CD tutorial MPI leaks. And then we're now in the appropriate stage directory. So this is where Spack downloaded all the source files. And but Spack, when you do a Spack install, also sets some environment variables and loads other few things into the shell. So we can emulate that by using the Spack build env command. So you can do Spack build env tutorial MPI leaks, and then whatever shell program you want. So I'm just going to use bash for this. So we can use the configure command. So we'll do configure, and then we will use the prefix that MPI leaks is all the source files were installed to. So we'll just copy this here. And I just want to note that this should be the same as the directory that Spack told us about before. So we'll do that. And then we can see it runs through the same configure step. And it's still unable to locate the adept utils installation. So at this point, nothing has changed throughout our debugging. And we can go back and look at the README for how the build might expect um, dependencies to be passed. So it looks like MPI leaks specifically wants the installation directory of both adeptutils and call path to be specified on the configure line. A lot of other packages, if they have more robust build systems, will pick up on things like um, the autotools prefix or things like cmake prefix path that Spack automatically adds dependencies to. But if in this case, MPI Leaks is not set up to search for those paths. It wants adeptutils and call path, those installation directories to be passed directly into the configure step, which Spack won't do automatically because it doesn't assume that it doesn't know which search paths or which parameters it needs to pass for packages to search in. So we're gonna have to make a couple changes to that, and just to show again and maybe learn a few other things about the build system that MPI Leaks uses, we can run configure help, and we can verify here under optional packages. With adeptutils, we need to specify the adeptutils path, and with call path, it wants the path to the installation of call path. And then we have another couple options that MPI Leak specifies that we could potentially turn into variants down the line if a user may want to install it in a different way. So, so this confirms, like, throughout this debugging process, starting with looking at the build log and then trying to do a manual build, we've confirmed that we need to pass the installation directories of our dependencies or already installed directories or dependencies with those options, with adeptutils and with call path. So just a reminder that we're within the spawn shell that was started by Spack env. So we'll need to exit out of there, and then we're going to change it back into our Spack root directory. So now that we know like which options need to pass into configure with adeptutils and which call path, we need to figure out how to determine the installation paths for those dependencies from within the package.py file. So fortunately, the package's spec, self.spec property holds the entire package's DAG of its dependencies. So each of the specs, each of the dependencies spec objects accessed by the name of that dependency, so call path or adeptutils, has properties that point it to the installation path of the dependencies. So we can use the information that we can get from that, the installation directories for the dependencies, and use a couple other Spack features to pass that information onto the configure step. So let's run Spack edit tutorial MPI leaks again. And let's add the with adeptutils and with call path arguments to the configure args method. So let's go down to the configure args, and then we're going to create a new list args, and then I'm going to create an f string with adept utils, and then I'm going to write bracket curly brace self.spec, and then we can access the adeptutils dependency here. And then the prefix property will get us the installation path. And we'll close out the quote there, and then we'll do the same for call path. So with call path equals self.spec, and then call path, and then dot prefix. Curly brace, quote. Okay, and then we'll close out this list. And then we'll delete these fixed names. So that should point Spack and AutoTools configure step to the information that it needs to pass the information about these dependencies to the package. So let's try to install MPI leaks now. So we'll do Spack install tutorial MPI leaks. So we can see that MPI leaks is going through its configure step again. It's taking a bit longer than it did before. Okay, so it moved on to build. It did the configure well, and it installed. So what we need to do was look at the build error that we encountered during our attempted installation. Notice that in this case, MPI leaks build system did not look in standard prefixes for the installation of its dependencies. It needed arguments passed to the configure step. And we accessed the spec object for the dependencies of the package to find where they were installed and pass that information on. So let's move on to the next step here, which is you have a successful installation with the default options, but let's say some of your users, some of your users or you yourself want to use some of the optional features in the package. And in Spack, we do this through adding build time options with a feature called variants. So if we look back at the output that we saw in the configure help command that we ran when we were doing our initial debugging, we saw that we had a couple of these options with stack start and for both C and Fortran, which essentially when MPI leaks is looking at a stack trace, it will shave off a couple of the top values for analysis. So this is just an option that a user of MPI leaks may want to use when they're using the software. So let's expose it with Spack using a variant so that the software works in a way that they want to. So in order to do this, with Spack, we will add a variant directive, and then we will change the configure options to use the value of that variant. Like we did in the modifications that we made to pass the installation prefix with the configure options, we'll do something similar in that method. So let's go back into Spack edit tutorial MPI leaks. And then we're going to add a variant directive here. So we'll do it after version. And I'm just going to minimize this to give us a bit more space here. So we'll do variant, and then we'll call the variant stack start. Just to keep it simple, we'll do one variant for both the C and Fortran options. And then we'll make it an integer, and then we'll make the default 0. And notice that we're making the default a string. And then the description, we'll say specify the number of stack frames to truncate. And then we'll close this, close this out. And then we'll move on to the configure args method of the package to propagate the stack start variant onto the configure args. So we'll initiate, okay, we'll do stack start, and then we'll recast the variant value back to an integer because that's what the configure args expect. And then we'll access the value of the variant by running self.spec.variance, and then we'll get the value of stack start by running stack start and then dot value. Okay, and then because the default value is 0, we can check if the user has made a modification to the stack start variant by checking if stack start with Python, because this will evaluate to false if it's set to the default value of 0. And then we'll extend the list, the args list, with our new arguments. So we'll do f and then with stack start c equals stack start. And then we'll do the same for with stack start Fortran. Is stack start Fortran equals stack start. Okay. So, oops, I forgot a comma there. Okay. So let's close out the extend. And then this should be the extent of our modifications to the package.py file. So just to quickly recap what we did to add a variant here, we specified the name of the variant. We specified the type. So we need an integer in this case. We said the default and then the description. This will be information passed on to commands like Spack info. So a user could run Spack info, MPI leaks, and see, okay, these are all the variants that I can specify when I'm deciding to install the package. And then using the variant value, we propagated the information back down to the configure arg spec, which will be picked up during the build installation of MPI leaks. So let's close out of the package now, and then we're going to install the package again. So we'll do Spack install, and then we will do tutorial MPI leaks, and then we'll specify stack start equals 4. And just a quick note on what you see here in the tutorial, web page verbose will not automatically start a verbose installation. Due to the new installer, you'll need to have this installation process begin. And then once you see that tutorial MPI leaks is starting to install, you can hit the V key on your keyboard, and then that'll pop up all the logs that you need for that you can see when the package install is actually happening. So clicked V, and then we can see the configure step is happening. And we'll do this, having verbose output is useful when you're doing things like adding a new variant, adding a new dependency, because you can go verify that those new arguments are being passed to the appropriate phases of the installation. So I'll just do a Command F, and then I'll see, let's see, stack. Let's see, do a search for stack is, okay. So we can see that with stack start C equals 4 and with stack start Fortran is equal to 4. So Spack installed our package successfully with this new variant that we specified. So now you've learned how to use a variant to add a pretty simple build time option for your users and for your package itself. And a couple other things that I want to touch on regarding creating your own packages. Build recipes, because of the generalizability and the fact that you want to be able to build this on multiple systems and multiple architectures, the build recipes are going to need to change. And that's where you can do things like checking how the package's dependencies were built, what compiler was used to build the package, what version of the package is being installed, doing some conditional logic based on the versions, on the variants that were specified. And this just allows more flexibility if you as a package author or the maintainer of a software know that there are some intricacies that you need logic for when you need to condition the build on some of these other pieces of information that Spack will expose. So I'm just going to run through a few of these. You can check with the self.spec.satisfies method here to see if the package that we're building is greater than version 1.1, so you might have some conditional logic you need there. Same if you want to check which compiler was used for the package. So you may have something you need to do if the package was built with a compiler at or less than GCC 5.0. You can check for the version of a dependency. So dynast, you can see if it's at least version 8.0, and then you might need to add a couple build options to your package. And back to what we were talking about regarding providers and virtual dependencies, if you are just doing depends on MPI, you may not necessarily know in advance which MPI implementation is going to be used to build a package. And you might have a couple build flags or some things you want to change in the package if the MPI implementation is OpenMPI. So you can do that check by looking at the spec object for the MPI virtual. And you can also do things like check whether or not you're building with the debug variant. And you can do things like add the G option to your configure flag so your compiler adds those symbols into the package. And these are just a couple examples of how these spec object queries work. Spack has thousands of built-in packages that have a pretty big diversity of build systems. There's, as we'll talk about in a second, packages can have multiple build systems. So the complexity that's already in Spack for those existing packages is quite broad. And you can take a look at the Spack packages repository, and we have a couple helper commands like we already saw, Spack info, and then you can also do Spack package grep to detect some of the patterns that you may have in your software that you want to look at for inspiration on how to package your own, how to build your own package. So the last thing I'm going to walk through here is a case where your software may have two different build systems. So in the case of this Uncrustify, which I think is a source code prettifier, you may have this case where you build with auto tools up to a specific version, and then you decided to migrate to CMake after that version, but you still want Spack users to have access to both of those versions and be able to build with either of those build systems. So in this case, you would import both of the package classes for those build systems, inherit from both of the classes, and then you would add a conditional onto the build system directive saying CMake will be the build system when it's over 0.64, and then auto tools below. And then you can also do things like have dependencies that depend on the fact that you're using a specific build system to install the software. So another difference is that when you are using multiple build systems, in our baseline package or in our example package, we were able to just do things like override the configure args method in the package directly. But when you have multiple of these classes, you'll need to use these builder classes and override the argument setting methods within them. So they're different for CMake and for configure and for auto tools. So as we finish this subsection of the tutorial up, I want to make sure that we don't interfere with subsequent sections of the tutorial or anything else in your Spack instance. So let's uninstall all the versions of MPI leaks that we installed today. So we'll do Spack uninstall AY and then tutorial MPI leaks. So that'll uninstall all the versions and agree by default. So Spack will prompt you. And then we will remove the repository that we created. So we'll do Spack repo remove tutorial. And we'll also remove the directory where those repo files were stored. Because Spack repo remove will simply unregister that repository from Spack. It won't remove those files. So we've gone through a pretty simple example of how to take a repository that you want to have packaged in Spack, walk through some debugging when the initial version of the package didn't work. We added some documentation about the package, so that is available for other users in Spack info. And we added variants and talked about what you might do if you wanted to support multiple build systems. The good thing is there are a ton of other resources um, for building packages. We have a pretty comprehensive packaging guide that goes through four different, higher level concepts within Spack packaging. And like I mentioned before, there are thousands of examples available for your use case based on previous practice by our maintainers. Um, and we have lots of links here that you can click on. Like if you wanted to make your package externally discoverable so that when you have a user on a system that can run Spack external find and it'll find a system built version of that package automatically. Or you can add tests to your packages, things like that. So I'll leave it with that and thank you.
I always love the packaging section because I think that it oftentimes when folks start using Spack, they start as kind of consumers of the tool and getting a lot of the benefits for installing software onto their HPC systems. But then at some point, you need some piece of software that's not yet in Spack. And a bunch of people, I mean, we have thousands of contributors now to the packages repo. And once you take this leap into learning how to write your own packages and then contributing them back upstream, it really is a big shift in the sense of community and the sense of how you're interacting with the tool. And also, if you're not sure about a package, if you've just started packaging something, I promise we don't bite. Feel free to submit pull requests to the upstream Spack packages repo, and we are happy to help you out and get your contributions in. So with that, I'll hand it back over to Greg.
All right. So earlier, I was talking very much from a facilities deployment or team deployment sort of perspective. How do I use Spack to deploy a bunch of software? We're going to go to the complete opposite end of the spectrum. How do I use Spack best to support my own development of software that I'm developing? And, Spack is a source package manager, so that's a good start for being a development tool. But the way that you interact with your source code as a developer is obviously very different than as a consumer of package releases. When you're developing, you want to iterate quickly on small changes, typically without changing the overall configuration of the package. A lot of tools like Make or CMake sort of support this sort of iterative buildup of configuration and compilation. And so we have some features in Spack to help support this sort of difference of workflow. We're not going to go out and fetch the source code and build it. We're going to build from a local source right here, and we're going to iterate it with it frequently before moving on. So we're going to start off the way a lot of these things start off. We're going to create an environment. We're going to add some packages. We're going to install them. So we're going to make a devel env directory. We're going to cd there. Spack env create -d dot creates an environment in the current directory. Spacktivate that environment. The first thing we're going to do is we're going to turn off Fortran. In a bunch of for some variants. And this is because for this section, we're actually going to have to do installations from source. And the packages that we're working on install pretty quickly, but they install even faster if we don't enable the Fortran support in them. So that's just to make sure we keep that off. And we're going to add maxio plus scr to this environment and Spack install. And so for the rest of this section of the tutorial, we are all going to pretend that we are developers for SCR. SCR is a library for scalable checkpointing for HPC applications. You read and write checkpoints to high bandwidth local file systems like RAM disk or a burst buffer, and it does file integrity checks across nodes over MPI. And we're going to be working with Max.io, which is a proxy app that mimics some HPC IO workloads and has SCR support as part of that. So we've got our environment installed. This all pulled from binary caches. And we will do a Spack find -cv SCR. So here is our concrete SCR spec with all of these variants, some default cache locations, the relative path of the config file, etc. And now let's start working as a developer. So the key command for this is spack develop. And the spack develop command is going to do two things. First, it's going to set up some develop config that tells us, okay, one of the packages that we are developing in this instance is SCR at this particular version. And actually, it's doing three things. I misspoke. It's setting that up. It is cloning the source for that version of SCR. Now, there are options that we could say, I already have my source code over here, right? I've been developing this. I don't need Spack to clone it for me necessarily, but if I don't say anything, I'm going to get a clone of it. And it's going to modify the SCR spec. So if we do a spack find -cv SCR now, there is this additional variant. So provenance for developer builds is a little bit tricky. With a normal Spack build, we know exactly what we're getting. With the developer build, we're getting something roughly based on this version, but we don't know how much you've changed it. Theoretically, I could make exactly the changes that turn this version into the next version, but this is still the version that Spack knows about. So for provenance, we just say it's around this version and it came out of this directory. You're not going to want to make a binary package out of that, but it's enough to keep your build separate. And we're going to get a new hash for Max.io. So if I do a spack find -c v Max.io, right? It's not installed because we changed the spec for its dependency. We haven't reinstalled the new one. So now we can spack install. And Spack says, okay, I need this build dependency for SCR, that's CMake. And now my SCR source code my SCR spec has changed. I need to reinstall that, and I'm going to do a source installation of Max.io on top of that. So now, okay, great. We're building from local source. How do we iterate on this over time? So we are going to edit our package or our software, right? We're developers. We're making all sorts of edits. Most of the time as developers, we are also introducing bugs. So that's what I'm going to do here intentionally. So I've just gone into this file and deleted the first semicolon in a C file. So we've made some changes to our software. And now we're going to spack install again. And now Spack is going to operate a bit more like make. It's going to compare the modification time of our SCR source to the installation time of our SCR package. And it's going to say, oh, this is a package that's being actively developed, and it has changes since the last time I've installed it. I'm going to go do an overwrite install. And in this case, that's going to fail, obviously, because we deleted a semicolon. So we saw some stuff earlier about debugging, right? We could look at the build output.txt. We could look at the build environment. We could drop into the build environment like Caetano showed earlier in the packaging section. But we don't need to do any of that. We know what happened. We're going to edit scr/src/scr_copy.c again. It helps if I don't create typos on the command line. And we're going to fix our bug. It's the other thing we do as a developer. We create bugs and we fix them. And I will Spack install again. And again, Spack saw that there were newer changes, rebuilt it, and rebuilt Max.io as expected. This iterative build process works differently depending on which build system you use. Build systems that are natively iterative, like a basic, like a standard sort of makefile package or a CMake package, those work very cleanly for this. It'll take a little bit longer with an auto tools package because there's no caching for the results of configure for an auto tools package. So you get the whole configure phase run over again. That said, Spack will still check the modification times and know whether to trigger that process at all. So that's developing a package. Now, often we actually want to co-develop packages. I modify my application, and when I make that modification, it exposes a bug in a library. I'm going to then go and modify that library. Or I change my library and I know that I need to make changes to an application that I also develop that depends on it. So in this case, we're going to follow that second model. We're SCR developers, and we also work on Max.io, and we might want to also develop Max.io at the same time to keep up with our API changes or something like that. So we're going to say Spack develop -- recursive SCR. So, okay, we're skipping making changes for SCR because we've already done it. We're now getting the source code for Max.io as well. And we can now Spack find -cv Max.io. And we can see that the develop command also updated it to have this dev path variant. So the develop -- recursive option can only be done in an already concrete environment to know what the dependents are. In this case, right, we only needed to develop one more thing. We could have just said Spack develop Max.io and it would have done the same thing. That's all great for working on my own, but I might want to set up a development environment for someone else. I might want to give them my environment to reproduce a bug, or I also might want to set up a development environment for my team so that we are all starting from the same starting point. So we can pre-configure a development environment. Spack. Well, first we're going to Spack develop SCR, and we're going to try to change the build type to debug. And Spack's going to say, I can't do that. Build type equals debug is incompatible with what's already in the package or in the environment. So we can say Spack develop -- no modify concrete specs SCR build type equals debug. And that's just saying, okay, don't try to change the spec. I'm going to do a full reconcretization of the environment before I get developer builds for this. Now, we might actually want a different version, so we can also modify the version while we do this. We're moving to a newer version of SCR. And now, once we've made all of these changes, we can Spack concretize -- force, Spack concretize -f, do a full reconcretization, and that will apply all of the changes we've made, since we couldn't apply them as we went because they were more complex than just adding in the develop path variant. Couple things to keep in mind with this. Spack add will help you make sure that you have the right version in the environment, right? If you just add the package, you might get a different version. If you do a Spack add with the correct version, you can keep it consistent. If the spec is not already concrete in the environment, you absolutely have to provide a version, right? Generally, when Spack fetches source code, we know what version it is from a concrete spec. If we're trying to do that from an abstract spec, it needs to have a version. The rest of this, I think we've already talked about. Yeah, you're in charge of managing your source code now, right? Spack might clone it for you the first time, but if you go and check out a different branch, you're going to want to update your clone to say that it's this other branch, right? I just updated my specs to say I'm installing SCR at 3.1.0, but Spack did not go and change the source code for me. Now I'll talk more about sharing development environments. So if I want to share this development environment, I'm going to make a new directory. And this is just to simulate being, another user, hand it to someone who doesn't already have it. I can copy this existing environment, copy the spack.yaml over to my current environment, and I can just Spacktivate it directly. I don't need to do anything special to make it an environment. It already is a Spack environment because I copied a spack.yaml into it. In this directory where I don't have any of the code, I can say Spack develop with no additional arguments. I'm not trying to change what we're developing. I'm just saying Spack, set me up the development environment for this, or set me up to be a developer working with this environment. This environment already had develop information in it. And so Spack went out and cloned the version of SCR and the version of Max.io that we were developing. If I'm done developing them, I can say Spack undevelop SCR Max.io, and it will modify my environment. This will not remove your source code. You don't have to worry that Spack is going to delete your source code just because you've linked it up with Spack. The develop command will clone it for you if you need it, but undevelop is never going to delete it for you. That's the crux of it. We've got some optional tips and tricks, right? There's the help for the Spack develop command. So Spack develop dash dash help. And I've talked about some of this, right? I can tell it not to clone. I can tell it, here's where I already put it, or here's where I want Spack to put it. The force option would let me blow away an old version and have Spack clone the new one if I wanted to do that. So with these options together, I can say git clone my my software, and Spack develop, set the path to where I put it, and not rely on Spack for that checkout. A lot of this we already talked about for debugging in the packaging section. Obviously comes up all the more with developing your own software. You can drop into the build env that Spack would use using the Spack build env command. As you saw it before, you can run a singular command here, or you can just drop into a subshell. And this is a sort of typical workflow, right? Spack build env scr. Right, Spack develop scr because I already undeveloped it, or I'll go back to my other environment. Cd /devel env Spack dev dot, right? So I'm back in my environment. Spack env status, Spack config blame develop, and Spack build env scr. So I haven't installed my environment, so it won't let me set up the build environment. Because the build dependencies are missing. So I would have to tell it to install those. I'm not going to go through all of that live, but that'll allow you to iterate in that build environment. And when you run make in that subshell, it's running it through the Spack compiler wrappers and everything else that you've seen Spack do. All right. So the last thing I'm going to talk about is combinatorial development environments. There's a lot of times that you want to build your software that you're developing against multiple compilers or against multiple backends or something like that. Obviously, if you're going to do that, you need to set unify to false, because you can't put them all in the same environment. And then you can use the Spack change command to swap between them. So Spack change max.io build type equals release. Okay, so now I've swapped it back from debug to release, and now I can add plus scr build type equals debug. So now if I do a Spack find, I'll Spack concretize first. But then we'll have the two different builds here. We could do most of our development. We could do say, development with the debug build until we've ironed out the bugs, and then switch to the release build to do performance testing. I forgot to set the unification semantics. But right, we could do performance testing on the release build and debug correctness errors on the debug build, or things like that, that would take advantage of having these two builds around. All right. With that, I am going to hand things off to, I believe, Alec for the binary caching tutorial.
Yeah.
All right. Not exit. I'm going to despacktivate to get out of this environment that we were just using. And then we'll move forward with binary caches.
And so we've been using binary caches all throughout this tutorial. We added really the tutorial binary cache right in the very beginning of the basic section. And then we've been installing pre-built binaries out of that build cache throughout all of the sections so far to make the builds go faster so that we're not here, spending 30 minutes building up to a large stack. Which has gotten much better in the parallel installer. We've heard from folks that, installing large stacks of software is now faster than ever, but still not as fast as we would want it to be to give live in a tutorial. And so this section is going to teach folks, I guess all of us, how to use and create our own binary caches that you might want to either push up to, we support an S3 bucket or S3 interface. You can push to a local file system, and you can also push to an OCI build cache, which is what I'm going to demonstrate here. An OCI build cache is something like Docker Hub or GitHub Packages. It's the Open Container Initiative standard. And it's very handy that we can also push back to this because it's often available for lots of sites locally have GitLab instances, and your GitLab instances have a GitLab registry associated with them. That is a really handy place to store binaries, both so that your team can access them with their typical GitLab credentials that you're using for properly pushing and pulling code at your site, but also so that you can reuse them inside of CI/CD workflows to speed up those workflows by a lot instead of having to install all of the software from source every time you run your workflow. Now you can reinstall 98% of your software stack through binaries every time, and then just rebuild the couple of things that change over time or your top-level application, like if you're doing a developer workflow, like Greg was just showing. So to get started here, I'm going to go ahead and create a new environment. We're just going to call it my env. So I'll go ahead and run make dir my env, and then we're just going to cd into that directory. And here we're going to create a super simple environment with Spack env create. We're going to create it with a view right in the directory. So here I will use with view. We're going to name the view view, and then we're going to create the environment in this directory. Like we talked about yesterday, this is what we call an independent environment. And they are environments that you can push up to Git repos, sync with the rest of your team. So it's going to go ahead and create that Spack YAML file right here. We're going to run spack-e with a dot. This means I want to load Spack with the environment that's present in my current working directory. And now, instead of having to do spack env activate, before running this command, we run -e with the environment that's currently in this working directory. Then we can just add Julia straight to that. And now we'll go ahead and run spack-e dot again, install. We're just going to install Julia and all of its subcomponents. So that went ahead and concretized. Now we're pulling them all from the tutorial binary cache that we've been using previously. But the next section, after we install Julia, I'll give a quick demo just to show Julia working. And so that is, we can go into our view. If you just wanted to look inside of this, it looks like what you would see in a root file system for a Linux distribution. So inside of view, then in Julia, we can then go -E to execute a Julia statement. We're going to do println. We're just going to do a really simple 1 + 1 here. Oh. Oh, right. It's not doing the less on top of that. Okay, there. Now we see that simple 1 + 1 = 2. Great, so we know that we've got a working Julia installation here. Now we're going to create a binary cache and push this binary cache up to an OCI registry. First, let's create ourselves an OCI registry. And so inside of this virtual machine image that you all are running on, we've got Docker. And so we can run a OCI registry very easily just inside of a small Docker container using the official registry image that Docker provides. So here we'll do docker.run. If you all haven't used Docker before, don't worry about it. There are loads of great tutorials online for how to run Docker, but this is essentially, we're just going to run and instantiate a small container, and we're going to call it registry, and it's going to come from the registry image. -D means that we're going to run it as a daemon, so we're going to run it in the background. We're going to do -rm to clean up the container once we're done with it. And we're going to expose port 5000 from the container onto our host system so that we can push these containers. And then we're just going to use the registry image. Okay, so we didn't have the registry image locally. Docker went out to Docker Hub, pulled it for us, and it's now launched that container. If you want to go see that that container is running in the background, we can do Docker PS. They'll just show you a really quick which containers are loaded on your system and how they're configured with their ports. Now that we've got that set up, let's add our mirror to our Spack environment. So again, I'll do spack-e for the environment that's in this working directory. We'll add a mirror with mirror add. In this tutorial, we're not going to go through the process of configuring GPG keys to sign all of your binaries. This is, however, I guess, good practice if you end up creating a binary cache that you want multiple users to use and you're not just trusting yourself, but you want them to trust you. We do recommend going through the process, and we have lots of documentation on how to have Spack generate a GPG key for you and then sign your binaries after you build them before you push them up to a build cache. And then, as you guys saw in the basics tutorial, when you have somebody use your binary cache, you add the mirror, and then you also trust the keys. And that's something that we did yesterday, and then as we were resetting up the VMs today. But here, just to make that process easier, we're going to add the unsigned flag so that we're not signing our binaries here. We're going to call this my registry, and then to prevent typos from derailing us, I'm going to copy and paste this. But it's basically saying we're going to use the OCI protocol over standard HTTP, not HTTPS, to configure that upstream registry image that we used. We're going to create a container inside of that registry that is called build cache. So once we've added that registry to our configuration, we can see it by looking at our spack.yaml, just to harken back to how we talked about environments yesterday. So you can see that we have that mirrors configuration section here with the name of our registry, our URL, and whether it's signed. There are flags if your mirror can only be accessed with specific keys or tokens. There's a way to tell Spack about how to use those keys and tokens inside of your mirror configuration. Feel free to look at the documentation for that. But you don't have to put your actual mirror key inside of your environment. You can use something like an environment variable, and then as long as you populate that environment variable outside of your Spack environment, then we can reuse what's on your system without you accidentally leaking and pushing that key to, say, a GitHub repo. Okay, great. So now that we've gotten this section, let's go ahead and push up our Julia installation and all of its dependencies up to our binary cache. So here, just to save us time, I'm going to do Spack env activate with our environment, and then I'm going to run Spack build cache push. We're going to skip pushing up our build dependencies. If you and the without build dependencies flag is really to say you don't need your build dependencies when you're pulling from a binary installation. You might oftentimes still want to push the build dependencies so that you can reuse them and rebuild newer versions of your top level application, in this case Julia, without having to rebuild your whole stack. But if you were just building a binary cache for other people to use it, like you're publishing your environment or your piece of software, then you could use this without build dependencies just to trim down on all of the software that you're pushing and reduce your overhead or your costs, maybe if you're storing this in something like an S3 bucket. And then we're going to push it up to the my registry. And so we'll see that this goes ahead and it pushes each of our specs, each of our run and link time dependencies up to the binary cache that we've created, up to that OCI build cache. We'll give this a second. LLVM is a really big one here, so it's going to take a quick second to transfer over. And there we go. We've pushed all of them, and then we also tag all of them. If you all are familiar with Docker containers all have tags. Oftentimes, the most common one is latest, and that's a tag that moves over time to track the latest version of a container. Since we're somewhat abusing the OCI spec here, we tag all of these different layers in our synthetic container, as you can think about it, as the name and the hash of the package. And we do that so that then later we can go out and we can get a list of all of those tags and treat it as like an index, that then we know which layers to go and pull. And also, if we wanted to go rerun this a second time without doing anything, we can see that we're using that index. We're dynamically going out and looking at that index, and then we're able to know, hey, everything that we already have in this environment, it's already been pushed to the build cache. So this is really nice because you could be working with a common build cache for a while, and every time you do a push, you're only going to push up a differential of every new package that you've created. So helps you a little bit on bandwidth, and also doesn't blow out the size of your upstream like GitLab packages or GitHub packages instance with multiple copies of every layer. So now let's go ahead and I'm going to set my editor to Emacs real quick. Let's do Spack config edit to drop ourselves into our environment file here. And like we talked about yesterday in the config section, Spack config is almost entirely normal YAML syntax. The one extension that we make on top of it is the double colon, and that allows us to drop sections or drop layers of config below something like our environment. So here we configured our tutorial binary cache in our user scope. And so that would be inside of our home directory, inside of .spack, there's going to be a mirror config in there that points to our tutorial repo or our tutorial build cache. We want to not use that tutorial build cache when we reinstall Julia, and we want to make sure that we're only reinstalling it from our my registry build cache. And so here we'll use the double colon to drop any other mirror config from our Spack environment and only use this build cache. So I'll go ahead and save this. Oops. Drop out of here. And now we can forcefully go reinstall this with spack install -- overwrite. We're going to say, yes, I really want to do this. And then I want to reinstall Julia. And so we'll see that now Spack is fetching it from the build cache. It's relocating it, which really means that we're looking at the binary, we're looking for any hard-coded paths in the binary, and I'll talk about that a little bit more in detail later on. But then we're updating all of those paths to put Julia and make sure that Julia knows of all of its dependents are in the right place inside of those like art paths inside of the binary. So there we go. We've gone and pulled Julia from our OCI build cache, pulled it back down, and now we've got a Julia installation again. Where this gets really cool when we're using OCI build caches specifically is that we can now use our Julia installation on our Julia binary cache in the OCI registry as a container. So you don't even need your end users to have Spack installed to be able to use this. We can instead expose our build cache and rewrite the metadata a little bit to make it look like a container and then run that environment. Now, if we were just to do this with our existing build cache with no changes, we'll see that this actually fails because we haven't added the right metadata. So I'm going to go in here, I'm going to change the hash of our Julia instance a little bit to make sure that it is the version that we actually installed and pushed into the binary cache. But if we were to go run this right now, we'll see that it does pull down all of the layers, being all, in each one of these layers is our build or run dependency, or excuse me, our link or run dependency. But when this gets to the very end, we're going to see it fail. Wait for it to squash the image down or pack all the layers on top of each other into the overlay file system. But we'll see, here we go, that this fails. And basically, this container is incomplete as it currently stands. It specifies all the version or all of the instances of Spack software, but we don't have a base container to get us, an exec and all of the base level functionality that we would want in a runnable system image. Something like bash, you want something like exec, a libc. That's not something we currently model in Spack. It's a way that we're pushing so that eventually we could have fully bootstrapped Spack containers and you wouldn't need a base layer. But for now, when you publish a binary cache that you want to reuse as a container, you just add this additional flag base image. And here we'll do a base image of Ubuntu 2604 because this is the same as the virtual machine that we've been using. So I will go ahead and copy this command. We'll run it here. And now essentially when we push up our build cache, we're now updating the metadata to say we need to use that base image to get ourselves a libc, an exec, the base functionality, kind of all the core tools that we didn't build inside of Spack. But if we do this, now we can go back and download that container, and we should see it actually execute and print out too. And so this, again, doesn't require people to have Spack at all for that end-level consumer. You could do all of this work to push up your binary cache to something like GitHub Packages, specifying a base container, and then you could say, hey, other person on my team, somebody that needs to run my software, just run, just run Docker and run this Docker run command, and you'll be able to execute my software. So again, I'm going to go here and change our Julia hash at the very end of the Spack, because it's changed a little bit. Okay, there we go. Now you'll see it's able to reuse a whole bunch of those layers. We already had them, but it downloaded that base Ubuntu layer. It's going to overlay everything on top of each other. We should see this print out too at the end. This is a relatively new feature of Spack that came up in the past couple of years. So if you previously took a Spack tutorial and had used build caches with maybe the file system or an S3 bucket, but didn't know that we had OCI support, it's relatively new, but it's been a really handy addition. So there we go. Now we can see that it printed out too. So again, just a great handy way to be able to build up your software stack with Spack, then convert that software stack over to looking like a container, without having to separately run Spack inside of a container. So this allows you to reuse all the software that you've installed on your system already. It allows you to have a persistent cache outside of the containerized environment, but then take all of those layers, treat them as a container, and distribute them to folks as a container. So here, I want to show a quick example of, maybe you want more than just Julia in your container. You want a specific environment. So here, let's add them. And so I'll just do Spack add them, and then Spack install, since that's what we've been doing throughout this tutorial. This warning is fine. It's just saying that we create separate indices for concretizations to allow the concretizer to know what to be able to snap to. Oh, and I didn't re-enable the tutorial binary cache. That's fine. This is relatively quick to install for Vim. But just know this is going to install a couple of things from source. And if we wanted to, we could go delete that double colon in our environment configuration, and then we would be able to reuse our previously installed software inside of the binary cache. So once we go and build the software, we have this environment that now has both Julia and Vim. This is just a nice way to show that you can use the tag flag on the build cache push, so that then you can create a custom tag for your environment. Say this is my software stack, and this software stack will get you everything inside of this environment. It'll get you Vim, it'll get you Julia, anything else that you might want to be in that environment. And then when you share that and distribute that to other folks, you can say just run in this case, we called it build cache, but it's kind of the name of the container and then the name of the tag that has the metadata for all of the software that you want as part of your Spack environment. So, great. While this finishes up building, I'll talk real quickly about Spack Containerize. If you had used Spack previously before the OCI build caches were supported, you might have used something called Spack Containerize. We still support Spack Containerize. It is a way you can have Spack generate a Docker or a container file for you, which is kind of this format that folks might be familiar with here if you've used containers in the past. But basically, from a base image, we then copied in your Spack environment, built it. That system is really handy for integrating with existing tooling that you might already have that expects to be building something like Docker files, and integrates fairly nicely with CI systems in that way. But you do lose the persistent build cache of everything that you've previously installed on your system, or if you have a container fail halfway through a build, that container gets cleaned up, you lose your half of your build cache. And so instead, installing Spack outside of it using the OCI build cache does make those CI/CD workflows much nicer. You don't lose and have to repeat as much work. But we do know that some folks still really like using Spack Containerize, and it's planned to be around for quite a bit longer. One other note here, I talked about relocation a little bit earlier. And so inside of Spack, unlike a lot of other binary package managers, we relocate our binary installations to allow you to then install them into any arbitrary path. So if you've used something like Brew or apt Nix before, you'll know that they install software into very specific, with Nix, it's /Nix. With Brew on modern machines, it's opt-brew, I believe. And then apt is oftentimes installing something into like user ben or user lib, etc. Those all need to be in those very specific spots because inside of the binaries, they have hard-coded paths to their dependencies, and they expect their dependencies to be in very specific places. Inside of Spack, we inspect the binaries after we pull them down from a build cache. We look for those paths that look like R paths or strings that might be pointing to a dependency, and we instead rewrite them to link them up with the dependencies that we know about, so that that binary is then able to go find it And that binary and the dependencies can be installed in your home directory. They can be installed in an NFS file system, anywhere that you want to put them. The one caveat here is that when we relocate a package, it's much easier to relocate a very long path to something that's short. And it's very hard or nearly impossible to properly expand a path inside of a binary, because then you'd have to move a bunch of the rest of the pointers around. And so when creating a binary cache for Spack, we should go set this configuration option, basically the install tree padded length. And what this does is that every binary that you go create with Spack from that point on pads these paths inside of the binaries. So it makes your binaries a little bit larger, but not something that you're going to notice. But it pads them out to something like, in this case, we're doing 256 characters of space. That's a really long path. It's very unlikely that you're going to run into something that is longer than 256 characters out in a production environment. And so because we've pre-computed all of these or pre-built all of these binaries with the longer path, then later on when our users go and reuse them, because you're always going from a longer path to a shorter path, it's very easy for us to go and relocate and rewrite those paths inside of the binaries. So that's just a quick note there. One other note that we have is if you're using Spack inside of something like GitHub Actions and GitHub, we do provide a GitHub action that's called Setup Spack. This just makes it really easy for you inside of a workflow to go use Spack. And so if you do, this is GitHub Actions syntax here on the left, basically using the Spack action, it will go clone Spack, initialize a packages repo for you, and then anywhere after that in your inside of your CI pipeline, you can just run Spack, whatever Spack commands, Spack install my environment, Spack install, in this case, Python, and this will pull down those, or I guess will allow you to use Spack as normal as if you had cloned and configured it and set up the shell integration yourself. So just a little bit of a shorthand for folks. I will go ahead and stop this because it's taking a little bit longer than even I wanted for this to run. We'll go Spack config edit here. We'll drop the second colon from here. I'm just going to clean up this a little bit. Save this and let's go rerun this. We'll see that it pulls them and relocates it really quickly. And then we can run back up here real quickly just to say we can run this Spack build cache push and tag it as both Julia and Vem, just to show the example of that. And then if you pull down one of the Spack built OCI Docker containers and you don't give it a command afterwards, like previously we put Julia out here so that would run the Julia binary, if you don't do anything, it's going to drop you into a bash shell, which is kind of nice for an interactive environment where then you have all of your tools loaded. So here, we'll jump into here. You can see we're now root inside of the container. And if we wanted to, we could use them to open up like an example Julia file. And I'll jump out of there. We could also, use Julia as we would expect to normally open a Julia REPL, for example.
Yep.
So with that, that is the rest of the binary tutorial. Feel free to post questions. I'm happy to talk about binary caches and CI/CD systems all day. So if you all have questions, feel free to post them in the tutorial chat, or feel free to send me a direct message later on if you try this out in your environment and happen to hit a bug. With that, I'm going to hand it over to Caetano, I believe, who's doing the scripting section here at the end.
Okay, so to finish up the tutorial, coalescing all the features of Spack that we've learned about today, from environments to utilizing them to create software stacks, creating our own packages, using mirrors, as Alec just talked about. We're going to be doing some very simple scripting with Spack. As you begin to use Spack and you think of more complex use cases or want to integrate information you can get from Spack into some of your own scripting or some of your own workflows, the this tutorial will show how to get access to some of that, what you might think is internal information, but is actually quite accessible given the abstractions that are provided by Spack. So far to find a list of packages that we have installed, we've been using the Spack find command. So you can do very simple Spack find. It shows you the platform that the package was compiled for, as well as the compiler itself that was used to build the package. So you have that well categorized, and you know, it looks nice, but there's no filtering here. You kind of have to scroll up and down to see the way that certain things are built. So we'd like to see more functionality there. So you can have things in a more ordered fashion depending on your use case. So just want to show off some of the flags and arguments you can pass to the Spack find command to show your installed specs in a different format. So we can do this by passing the format flag to Spack find, and essentially you're just dictating the format of what the output of Spack find should be. So in this case, we want to have the name of the package come first, and then the version along with the first 10 characters of the hash. So you might want this to dump out into a script or a spreadsheet or something like that, and the format flag lets you do that quite easily. So we'll do Spack find format, and then quote name in curly brackets, version in curly brackets, and then hash :10 in curly brackets. And as you can see here, listed out in 2 columns in just the format that we expect. So you can combine the Spack find command along with the format flag with other commands like unique or sort to retrieve information that might be relevant to your own specific workflow. But this sort of just scratches the surface about how you can actually sort the Spack find command. And I just want to point out that the information that you actually pass to the format flag, these are all attributes of Spack's internal spec object. We've explored this throughout the tutorial. If you remember back in the packaging tutorial, we used some of this information to find out where dependencies were installed or what compiler our packages were installed with. So essentially, you can use these attributes, name, version, hash, other attributes. You can add those into your own format flag. And we have documentation that you can look at to see exactly, so you can find out exactly your own workflow and how you'd like to format the command. If you want more of a machine readable way to see your installed packages, you can serialize the spec objects of your installed packages in JSON with the JSON option. So you can do Spack find JSON with the JSON flag, and then we'll just do this specifically for zlibng. And you have all this beautiful information here about how the package was compiled, what it depended on, what its hash is, the version, etc. And you can pipe this to something like JQ or pass it into your own post-processing program to get more information about this specific installation. So that's some of the advanced usage of the Spack find command. Obviously, you can extend it a lot further than what I showed here today. But the next thing I want to move on to is the Spack Python command. So we provide this command that essentially launches an interpreter with Spack's modules, the Python modules that Spack exposes. We make those available for import. So the underlying Python instance that are used for all the other Spack commands that you use, with Spack find, Spack install, etc., you'll have access to that same Python instance with Spack Python. And that allows you to programmatically access the internals that Spack uses when it runs some of these common commands. And you can write your own scripts essentially in this way. I'll show you a quick example of how to do that. So I'm just going to clear my terminal here, and then just going to run Spack Python. And as you can see here, we launch a Python interpreter, the same one that's used in underlying Spack. We have our Spack version here. And just like any other Python interpreter, we can do exit to get out of here. So now we've left that Spack Python interpreter. So if you wanted to potentially use Spack Python to access the spec object, maybe to do, figure out, understand how the spec object is formatted so you can figure out how to write a package in a certain way and to express some logic that you might need in a package. You can do this by accessing the spec object within the context of Spack Python. So let's open Spack Python back up, and then we can import the spec class by doing from spack.spec import spec with an uppercase S. And then let's continue on with our zlib example. So let's assign a variable zlib, and then we will take this abstract spec zlib with a target of x86, x80, 86, 64, v3. So this, what we pass to the spec class is essentially an abstract spec like you would do with the spec install, define in a spec.yaml file, etc. So we can check if this spec has been concretized by checking the concrete property. So we haven't concretized it yet. Let's see if there's a resolved version for this. And no, because the spec hasn't been concretized yet, so Spack hasn't resolved what version should actually be used to install this package. We can continue verifying the fact that it's non-concrete by checking if the array versions is propagated, and no, it hasn't, along with the architecture. And other than what was passed in the abstract spec, x86, 64, v3, we don't have access to any of the other information because all we have is what we gave to Spack, and Spack hasn't concretized it yet. So none of those additional details are populated yet. But the good thing is we can use additional Spack methods to concretize this within the Spack Python environment or Spack Python interpreter. I don't want to reuse language there. So let's continue on. So we'll do Spack from spack.concretize, import concretize1, and that'll be used to concretize a single spec. And then we'll create another variable here, zlib concrete, to represent the concrete version of the zlib abstract spec that we were using before. And then we'll do equals spack.concretize, .concretize1, and then zlib. So as if you were doing spack install, spack concretize, this is what's happening under the hood. And once this finishes up, we should be able to access zlib concrete along with some of the additional properties that are not populated. So let's confirm that it's concrete. Let's check if there are any versions that Spack detected. So zlib concrete.version, version 1.3.2, and then let's check the list of versions as well. Zlib concrete.versions. So yeah, Spack found the versions are just this 1.3.2 that we saw earlier. And then let's also check what architecture this spec will be installed for. So yeah, I filled in some of these details, Linux along with the OS that this VM is based on, along with the architecture itself that we provided to Spack earlier, and which is what Spack used to concretize the spec. So we can do some more powerful queries. So let's take a look at an example that essentially shows how Spack find works under the hood. Spack find queries Spack's internal database, which stores information about all the installations along with other details that Spack uses during normal use. So let's import the Spack database objects. So let's just import spack.store, and then we can get some details about what information we can access here by using the built-in help function from Python. So we'll do help spack.store, and then .db.query to see what information we can get from the database. So taking a look at the first couple arguments here, we can pass a query spec. So we can pass an abstract spec that Spack will search for within the database. So maybe let's use this to do some simple queries within the Spack database. So if you remember with Spack find, you can do queries of attributes / abstract specs that match those specific values. You can't find packages that don't meet a certain condition. So for example, you can't do Spack find this package is not built for this platform, or this package was not built with this specific compiler. So we can use the Python interface to build on some of this logic and write custom queries that might be useful in your own workflow. So let's create another abstract spec with the built-in spec class. So we'll define another variable gcc query spec equals spec, and then gcc. Oops, missed a parenthetical there. Okay, so now we have that there, and then we'll build on the Spack database query method to do a search for that abstract spec. So we're going to look for all packages that have been built with GCC. So GCC spec equals, or GCC specs rather, equals spack.store dot uppercase store dot db dot query, and then we'll do GCC query spec. Okay, and then let's look for our result here. So we'll do some list comprehension spec for spec in GCC specs if not spec dot satisfies mpitch. So we'll finish that up there. Then yeah. Okay, so now we have a list of all packages that have been built with GCC that also don't depend on mpitch. So this is, not a great format to look at this information, but we also have another Spack helper function we can leverage here to display them in a way that you might recognize. So we'll do import spack.cmd, and then we'll do spack.cmd.display specs, and then using that result list that we created before. So now here you have the same exact way that you'll see the format as if you did a Spack find. So here we have the output of a query where we looked for all the packages that were built with GCC that also were not built with mpitch, using some of the helper functions that Spack allows you to leverage within Spack Python. So now we have like this more powerful query that you wouldn't normally have available through Spack find. And if you weren't aware of the scripting functionality, you might have some trouble. Go look manually through each installation, see what was installed with GCC, what depends on mpitch. So this just makes it a lot easier to do searches for packages that you might be interested in finding within your installation. So in the interest of time, I'm not going to do a walkthrough of or a live run of the rest of the tutorial, but I'm going to talk through what else you can do, what you can build on top of. So we can take what we wrote in the Spack Python interpreter use the same calls to the helper functions that we used before and add that to like a script, a Python script that you can have, in your own workspace that you can call repeatedly. So you can do this by creating a Python file, find exclude, importing these same Spack modules, and then repeating the logic that we were using before. So we have an include spec, which could be something like I want to check for packages that were built with GCC, and then exclude for packages that don't satisfy another constraint. So packages that were potentially built with mpitch. So you can take that all together, perform the query, and then use this display specs method to print it out in a nice way. And then you can run the new script by using Spack Python again. So you basically call the script along with its arguments with Spack Python, and then it'll display the same thing that we saw before. So you can also avoid the use of Spack Python by using the Spack Python executable. So you don't necessarily want to have to tell people, oh yeah, every time you want to run this find exclude script, you have to run Spack Python before. What if their environment isn't really set up in a way that allows for easy use? You can essentially add a shebang line to the first line of the script to allow it to be run as an executable. And there's an important edge case or pitfall that I want you to be aware of if you're going to be doing this sort of thing. You have to, so let's say you proceed normally, you add Spack space Python to the shebang line, you add execute permissions to the file, and then you execute it in a way that you might think would work, but you hit an error. So certain operating systems only support a single argument on the shebang line. So we have a Spack-Python executable. That's essentially a wrapper script for Spack Python that solves this issue. So if you hit this error when you're writing scripts, you'll need to do Spack-Python on the shebang line so that your operating system processes what it needs to execute properly. And then at that point, you should be able to do find exclude along with the filters that you specify, and that should work to get the output that you requested. So with these tools, you can create lots of other scripts. Like the sky is the limit here. You can filter on any of your installations. You can do concretizations. As you start exploring more features in Spack, I would encourage you to look in the Spack source code if you're interested in certain features that you might be interested in Spack. A lot of features start off as extensions or scripts that leverage Spack Python, and they ultimately make them upstream or exist to wrap Spack for your own specific use cases. So we always encourage this for users and people who use Spack heavily on a regular basis to find out what the pain points are, see if there might be an improvement to the way Spack works. Use Spack's internal tooling to maybe develop a new feature, and then if you can get consensus around that, you can potentially get that upstreamed. But it's also a good way to understand how Spack works under the hood, and if you encounter any issues or think of new features, it's pretty easy to get started and work through the Spack code base there. So I think that's the end of the tutorial here. Unless Alec or Greg have additional comments, I want to thank everyone for coming today. As always, you can check out our GitHub repository on github.com/spack/spack. Our packages repository hosts all of the 8,000 plus packages that are available to all our users. You can join us on the Spack Slack, so go to slack.spack.io. And we have a huge community there. I think over 4,000 people are always willing and able to answer questions. We have different channels for different topics, like environments, like Concretizer, core features, along with our continuous integration infrastructure. And yeah, so thank you for coming.